The LG Procast is intended for informational and entertainment purposes only. The views or opinions expressed by the podcast hosts and guests do not necessarily reflect the official position of LG. For the latest and most accurate information about LG products, please consult relevant product manuals and related documentation.
Hello and welcome back to another episode of the LG Procast. I'm Philip Craigbaum.
And I'm Terry Frisenda. Today we're joined by a very special guest to talk about probably one of the most or least hottest topics in the HVAC trade, and that is the changing of refrigerants from 410A to something new. Joining us today is Dr. Charles Allgood. Welcome, Dr. Allgood.
Oh, thanks for having me. Let me give you a little background. I've been in the HVACR industry for over 30 years now. I started out with DuPont Company, the ones who invented Freon, and got involved in the middle of the transition away from the CFCs to the HFCs. So we were moving from things like R22 to 410A. So I'm a chemist by training. I spent a lot of time in the lab, but then in the later part of my career, I'm out doing training, talking about a new generation of refrigerants and everything that's going on in the industry today. So glad to be here with you guys.
Yeah, we have the opportunity, or at least I have the opportunity to. This will make my second official refrigerant change, going from R22 to R410A, and now R410A to one of the new A2L refrigerants, as they're so called. Can you help us learn? I know you will. Can you help us learn a little bit about what's going on, why it's going on, and let's just have some good old conversation about what's happening in our industry.
Yeah, absolutely. Like you, I've been in the industry, over 30 years, and I came in right about the time we were transitioning out of the CFCs into the HFCs. So the R22 transition to 410. We learned a lot of things. There was a lot of, fear in the beginning. I think we overcame a lot of that in the industry, and so we're going through it again. Most of it is environmentally and regulatory driven. So there was issues with chlorine-containing refrigerants and ozone depletion. So with some of the international agreements, the Montreal Protocol, the industry moved to the HFCs. Then concern over global warming, climate change, you want to call it. The transition now to go into lower climate impact, lower GWP refrigerants, which moves us into the mildly flammable A2L category. So that's where we're going. The regulations are driving it, and we can get in some of the details there if you'd like.
So let's start right there with, I have this big note written on my pad here about, the scare mentality, because you use the word, slightly flammable or flammability. And I think there's a lot of misinformation around slightly flammable and flammable refrigerants. So can you just help us there understand a little bit about that particular point?
Yeah, absolutely. And historically, most of the refrigerants we've used have been what we call non-flammable. If you go by the strict language of the codes, it's no flame propagation. That has to do with the methodology we use to test refrigerants for flammability. So most things, 410, 22, 502, 404, 134A, all considered non-flammable. And the only flammables the industry really was exposed to was propane or butane. And those were very limited systems, very small charge sizes, 150 grams, factory produced, not a lot of service in the field. So we really haven't dealt with flammables much. And so we had that class 1, the non-flammables, and the class 3, the highly flammables. So we're now in this middle ground, which some people call mildly flammable. Or the ASHRAE standard, they go by lower flammability, but they are very, very different. And some people say they're more like the non-flammables than they are like propane, but there are certain, code standards, precautions, trainings that have to take place as the industry moves to adopt those.
Yeah. So obviously the technicians that are out there listening, and they hear this mildly flammable, or a homeowner listening, what are some things that maybe you can explain to them about what is different, because we say 410A and all these others are not classified as flammable, although my understanding is technically they are flammable just at a very, very low rate. As you said, there's no flame propagation. But what is the difference in a day-to-day life, how do they need to change their practices to be safe with these new refrigerants?
Sure. Yeah, and it goes to some of the, the basic properties of the molecules, the gases themselves. And so we look at a number of different things, one being the what's called the lower flammability limit. How much of that gas do you have to have? How big a concentration? How much fuel do you have to form a mixture that will be ignited? And that translates back to charge size and leaks and that kind of thing. So that's why the charge size on something like propane was so low. The assumption being if it all leaked out, you still weren't going to get to a dangerous level that it could be ignited. The A2Ls have much higher flammability limits, so it will require a much bigger leak. Therefore, you can have more reasonable charge sizes, and you can put it into things like, air conditioners, split systems, even chillers. One of the other things we look at is something called the minimum ignition energy, and this is a big differentiator. How much of a ignition source will it take to ignite this stuff if you have a mixture that could become flammable? So then you're comparing, for the A2Ls, it really is going to take a strong ignition source, something like an open flame or a torch. Things that could light off propane are a class 3, like, a static spark or, a electrical switch or something like that, or a sparking tool. Those are not going to be competent ignition sources for the A2Ls. So you have a much bigger safety factor there. Then really what defines the A2L in the standard is something called burning velocity. How quick the flame propagates. Does it burn more like a birthday candle or go off like a blowtorch? And we have videos, and there are other people who have videos. I encourage your listeners to go online and search some of those out where people are actually lighting these things, and you can see what the flame looks like. Like in A2L, the burning velocity has to be below 10 centimeters per second. I think for something like 454B, which is a blend of R32 and R1234YF, the burning velocity is around 4 or 5 centimeters per second. So just put that in perspective. You can walk faster than that. So you can see that flame. It's very kind of lazy flame. And then I would say the last real engineering factor that we look at is something called heat of combustion. How much energy is given off when this thing does burn? And again, is it like throwing a log onto a burning bonfire, or is this something totally different where you have a huge fuel source giving off a lot of energy? And so in all those cases, the A2Ls are going to be a lot more like the A1s. Very difficult to ignite. You need a pretty good leak to get to even a flammable concentration. And then even if they do burn, you're going to have a much less severe ignition event, as we would call it, just because of the energy of these molecules are different. So that's kind of puts it in perspective. If you have non-flammable class 1 on one end and a highly flammable explosive, propane, acetylene, butane on the other, A2Ls are kind of in the middle. But a lot of our handling, our guidelines and best practices are going to be very similar to what was done with A1s. For example, purging with nitrogen when you're brazing or something like that, always been suggested a good practice. Now it's going to be more required. And we can get into some of the other things on the equipment here if you'd like, on what's going to be a little different there. But for the handling procedures, it's going to be pretty simple. Most of the tools will be the same. The equipment, things like vacuum pumps or recovery machines, people are going to want to make sure they have one of those that's A2L rated. Those are out there, but your wrenches, hand tools, a lot of that stuff's going to be no change for the technicians working in the field.
Gotcha. So you did mention a little bit about equipment, and I know what I've read to date is equipment manufacturers are having to make changes in their equipment for safety devices and things like that. Can you help me better understand that from a chemical manufacturer's perspective?
Yeah, sure. And this comes into each OEM, each equipment manufacturer can approach this in a slightly different way. But for the most part, we want to avoid ever getting to a leak that would result in a flammable concentration. So the big thing I think we're going to see is more sensors on the equipment. So if a leak occurs, the sensor will detect it, and then it will take some action. It will, shut the machine down. It will probably may close a valve or two here. It may turn on a fan to disperse the gas, and so that's going to prevent any leak from becoming a problem based on continuing to build it up. So I think that is the biggest thing on the equipment side is going to be the sensor and the mitigation, and that will vary from equipment manufacturer to equipment manufacturer, but I think most of them are taking similar approaches. And if we get into more things like commercial refrigerant or walk-in boxes, it will be designed a little bit differently. But for your standard split systems, ducted systems, I think everybody's kind of going with a sensor and then mitigation controls following that.
So why the change?
I think the change mostly, as I mentioned up front, is regulatory driven. It's based on first international agreements, treaties like Montreal Protocol, we probably heard of, Kigali, and then each country enacts its own regulations. In the U.S., it was under the AIM Act, as we call it, the American Innovation and Manufacturing Act, that was signed late 2020. That basically gave authority to the U.S. EPA to make rules. And we've seen those rules come out here in the last years and months. And just to kind of summarize the AIM Act rules for refrigerants, it's really in three parts. We've seen two of them. The third one we're still waiting on. But the first one really impacted chemical manufacturers like Chemours who produce refrigerants. And it basically set in a timeline for a phase down of HFC refrigerants. Important to point out, it's a phase down, it's not a phase out. But year over year, every few years, we take another step down. So they set a baseline based on, I think, the average of 2013 to 2018 maybe. And then every year, not every year, but at every step down, we reduce from that baseline, which we got to remember, the industry is still growing. So we're stepping down and growing at the same time. But we went to 90% of the baseline a few years ago, and just the start of 2024, we took another 30% step down. So we're at 60% of the baseline and what we can produce. So that puts pressure on the higher, and that's all GWP weighted. So that puts pressure on higher GWP refrigerants like 404, 507, but things like 410 are not far behind. So that's kind of on the chemical manufacturer side. Then the second part of the regulations were what we call sector controls. That's by application. So if you're a supermarket, if you're a walk-in, if you're a big chiller, you're a residential AC, you're automotive air conditioning, all those segments have different GWP limits for new equipment. And so for air conditioning, kind of what we're talking about today, that limit's at 700, GWP 700. So 410 was at 2000. So the new alternatives are going to be less than 700. So it's basically R32 and R54B have been selected by the major OEMs. So that transition is starting, the beginning of next year. So the third part, which we haven't seen all the details, is around handling and reclaim and licensing and all that stuff. So that's going to be important as well. We just haven't seen the details yet. So that's why essentially the regulations are driving us to new equipment on more GWP refrigerants. That's how we got where we are today.
Do you think, I think back to the R22 phase out to 410A when equipment manufacturers, U.S. manufacturers, started producing these dry charge systems. In other words, shipping them with no refrigerant. Do you think that'll happen again?
I'm not sure. I don't think so. I think we had enough warning, and I think most of the equipment manufacturers that I'm aware of, and I don't talk to all of them, but I kind of see everyone's plans. I think they've been testing, 454B, R32 systems, getting ready to roll these things out. So I think everyone's ready to get on with it, honestly, at this point. I think we know that's the future. We're not going back. We're not, as much as some people would love to go back when they only had 3 colored jugs in their van. I hear that a lot. If I had a nickel for every time someone said that.
Yeah, right.
The good old days, we were not going back there. So I think people are ready to get on with it.
Are you talking about the days when I used R12 as a blowing agent for foam?
That might have been predated me a little bit, but yeah.
So we It was crazy. Selling R12 to do foam injection molding and stuff. It was insane, but that's what they used as a blowing agent. So anyway,
And
Philip.
it's just proliferated, right? So we've run out of colors. So we're not even
Yeah.
going to colors right.
Yeah.
Just make them all gray. Yeah.
Yeah, make them all gray. We go back to that comment you made earlier about split systems in the home, and the average size or the number one size of a U.S. split system is 3-ton, 36,000 BTUs. Is there enough refrigerant in that system, in a conventional system? I know on our side of the business we have less charge than most U.S. manufacturers anyway. Is there enough refrigerant in that 3-ton number one size system in the U.S. for a consumer to be alarmed or worried about from a flammability standpoint?
I think as the industry went through the changes to the safety standards, both in ASHRAE, like ASHRAE Standard 15, ASHRAE Standard 34, UL 2-89, 2-40, I think all those were considered charge size, releasable charge size, what the risk would be, how that mitigation would handle that to prevent coming to a flammable concentration, and then layering the protection on top of, no competent ignition sources, the detection, the mitigation, all has really handled those safety concerns or maybe initial concerns and in a way that consumers can be very confident that they should not have any concerns about this mildly flammable A2L refrigerants in those systems that are manufactured according to those standards and installed in the places and spaces, where the codes say they can go.
Gotcha. That's good stuff. All right, so help me understand. I know when we switched from 22 to 410A, there were some differences, and I think we used the word earlier when we talked about a little bit about fear or the unknown and the pressures. 32 and 454, we're talking specifically 32 because that's what LG has chosen for the refrigerant of choice for the U.S. systems and European systems. From a performance standpoint, what do we see? Is it more efficient, less efficient? What's the volume? What's going on there? Can you help me?
Yep, sure. Going back to the 22 to 410 transition for a minute. I mean, we were dealing with a totally new lubricant, right? We're going to POE from mineral oil. That was a big kind of fear. Oh, it picks up moisture. It's a good solvent. We got over that. We went from a pure molecule to a blend. And concerns about fractionation, is stuff going to fly apart, and how do we set the superheat? So I think we've learned a lot about handling blends in the last 20 years. We've learned a lot about the lubricants. I think those issues were probably bigger than the changes going from 410 to 32 or 454B. You got to have the flammability mitigation, and that will kind of come along with the equipment. As far as performance and charge sizes, they're going to be very similar. And 32 and 454B, have some differences, but not a whole lot, because remember 454B is a blend of 32 and 1234YF, so it has a lot of 32 in it. But capacity is pretty much going to be a wash if you have a good design on 410 versus one of the newer refrigerants. And energy efficiency, we expect, to be equivalent at least, and probably a little bit better, just with all the different, advances in designs and heat exchangers and optimizing compressors and all that technology we've just developed over the past few years. So I think performance-wise, they're going to be very, very solid. Everything we've seen suggests that those things are going to work very well, very similar to 410.
Yeah, I know. Speaking with contractors, one of the fears, frustrations, concerns that they're going to have, and you mentioned how many jugs that they're going to have to carry in their vans nowadays, is that when we went from 22 to 410A, everybody went to the same refrigerant, but now we're moving from 410A to either 32 or 454B. Maybe you can shed some light on why there's two. Why didn't all the manufacturers sit down and agree on one? We obviously chose R32, but maybe you can kind of give us a comparison. What are the differences between 454B and R32? I'm assuming that both of them have some pros and some cons, so maybe you can just kind of shed some light on that and help us understand why why we couldn't just have one new refrigerant going forward.
Yeah, it would make life a little simpler. And they are more alike than they are different. I mean, we're maybe not splitting hairs, but we're looking at some fine details in the difference. And I think the first one is GWP. R32 has GWP about 675. 454B is more like 465. So, a couple hundred points in GWP. When you're coming down from 2000, those might not appear to be that big a difference. I think that will come into play in the outer years of the phase down when we get squeezed more and more. And, we have to sell more and more pounds of refrigerant, but keep the same kind of total carbon equivalence at a reducing level. I think some of the OEMs viewed there was a longer runway out there in those outer years to stretch that out. On the plus side for R32, it's a pure component, so you don't have to worry about things that may impact a blend. Even though I said we're pretty good at handling them, like say take liquid out of the cylinder when you're charging or topping off. Use the dew point when you're setting superheat. You need to do those kind of things with a blend. You wouldn't have to do with a pure component like R32. And last, this is really not my area of expertise, but it's really the compressor guys have kind of said, 32 it's a small molecule if you look at its structure, so it tends to run a little hot. I would say. I think there was some work needed to be done on compressor development early on to deal with the higher discharge temperature of a pure 32 versus a blend, and maybe some lubricant development, some stuff around the hardware of the compressor. But that's essentially it. It's kind of a pure component with a little bit of higher GWP versus a blend with a lower GWP and operates slightly differently in terms of the hardware. But in terms of what the technician and what the homeowner and what the customers will see, I think they're going to be very, very similar. And, OEMs made their picks and the market's kind of split. I used to do a lot in supermarkets. It was like 404 and 507, kind of, I hate to say identical, but two refrigerants you probably couldn't tell apart if you didn't know they were different. And both worked well, and the market just split, and people adapted. And if you lived in a 404 world or geography, that's kind of what you dealt with, but you always could run into 507. I think we're going to see the same here. There's going to be equipment on 32 and a lot of equipment on 454B.
Any performance differences between the two charge sizes or anything like that? I mean, I've seen charts and read different things, but kind of wanted to get your take on that.
Yeah, I've seen some of that. I don't know that I can make a definitive statement one way or the other. I think it varies among equipment and design and manufacturer as much as it does between the two refrigerants. So, yeah, no clear answer, at least as far as I know. There may be more information I'm just not aware of, but I don't see a huge difference just based on the molecules themselves.
And I think I'm pretty sure I know the answer to this question, but what would happen if a technician put the wrong refrigerant into a system? So they run up on a R32 system and, oh shoot, I ran out of that stuff. So either let me fill it or top it off with 454B. What are we looking at?
Yeah, so let me just put it out there. Please don't mix refrigerants. We don't like anybody to mix refrigerants. And that's, I mean, we've always said that, and it's even more important now because reclaim is going to be really, really important. And so we really would need to maximize everything coming back through the reclaim channels, and mixed refrigerants just sometimes ruins that. For these two, since 32 is part of 454B, honestly, I don't know that you would see much of a difference at all if you were just looking at the machine run. That said, we don't want mixed refrigerants, and yeah, I don't want to be on record as telling people it's okay, but I don't see any disaster if that would happen, honestly.
Interesting.
You spoke earlier about when we went to 410A and fractionation. That's the correct word. With 32 being a single molecule, not that in the LG world it's a practice, but in the standard unitary world, topping off refrigerant has been a standard practice. It seems like if it's a single molecule with 32, that would be advantageous for that group of refrigerant users versus another blend and the fear of fractionation.
Yeah, certainly with a pure molecule, you can top off, if you need more charge in the field. In our experience, like I said, that was a concern early on, but in practice, and we can do detailed studies, and we have in the laboratory looking at the impact if this leaks 20% or worst case leak, when it's shut off and you have a very slow vapor leak, how much does it really fractionate, and does that impact performance when you top it off? And there is very detailed studies on that where it varies a percent or two, but nothing that is ever going to show up in actual performance. We're very confident in our recommendation. If you need to charge top up in the field, you can do that with 454B as you can with a pure molecule.
Gotcha. Okay, obviously from our perspective, we have such a small refrigerant charge as a general rule anyway. Leaks are detrimental to performance for us. So, our message, we want to make sure we go on record as saying our message is fix and find a leak, right?
Absolutely.
And then do a proper evac, and then let's get this thing charged correctly, because that's the way this stuff is designed to work, right? So,
Yep.
Yeah.
I know Philip and I
stand behind that 100%. Yeah. Find the leak and fix it. The days of just pouring more refrigerant top and running.
Can't do it. Yeah, can't do it. That's behind us, right?
For the environmental, for cost, for performance, for a number of reasons.
Absolutely.
So if we look at history, we know that we're only moving one direction, and that's to more and more and more environmentally friendly refrigerants. And while I believe R32 and 454B both have a pretty substantial runway in front of them, just curious to see what your thoughts are. Get your crystal ball out, and not necessarily a timeline, but what do you see coming after these refrigerants? Because I don't want to be naive to think that I'm going to have R32 for the rest of my career. What's coming down the road long term?
Yeah, that's a good question. My crystal ball is as foggy as a lot of other people's. I think the trends I do see, and across all HVAC is lower GWP refrigerant fluids, and we constantly are moving there. Lower charge sizes in general, reducing it where we can, and that's more maybe on commercial refrigerants than AC. So everything we can do around circularity, good recovery, reclaim, preventive maintenance, reducing leaks, I think is going to be important, keeping the gas in the system. Energy, I think, is going to be key going forward, which is why something like CO2 with a GWP of 1, hasn't just dominated our whole industry, because it's not very efficient. So you use a lot of electricity, you're just generating carbon emissions, at the power plant rather than through leaking refrigerant. So it's going to be interesting, because we're really, we came from GWPs of 4,000 or well above, and we're now talking, is it 700? Is it 150? Is it 10? Where's the final line drawn? I don't think anyone knows right now, but I think energy is going to be king, and then all the other controls, integrating heating. I think there's a lot of environmental benefit that can be gained with the refrigerants we have today, and still take steps without trying to look for a magic bullet. I think the one thing as a chemist, which I am, is I like to say the periodic table of elements, if you remember that from school, is not getting any bigger. But we want our refrigerants to do more and more. So now we want to be non-ozone depleting, low GWP, good capacity, good energy performance, non-toxic, lowest flammability possible, good materials compatibility, affordable. So we put more and more demands on the fluid. And so I think, we still have scientists in the white lab coats looking around at new molecules. Some of those will probably, get rolled out here in the coming years, and people can take a look at them and evaluate them. But I think more in my mind, the trend is like looking at the whole system and taking advantage of heat. I think the move to heat pumps is going to be big. I think, in the past, we ran a machine that generated a lot of heat. We just, rejected the heat where we didn't want it. I think we're going to have to get that heat and put it to work some way, somehow. So I don't know if I answered your question, but a lot of things circling around.
No, we certainly agree with capturing that wasted heat and using it. So we build in a plethora of products. Speaking of that, you know, we use 32 across our global platform, and we see a product, the air to water heat pump, which contains all the refrigerant outside in our product line and keeps it outside to maybe address some of that fear around, you know, flammability and stuff. So don't you think that's possibly a strategy as well, that we start to use water? And not that we haven't used water, but more predominantly use water as a source to satisfy BTUs and keep the refrigerant outside in a chassis. That's sounds like a pretty sound strategy to me.
Helps with leaks too if it's a packaged machine built in the factory, not having field installed joints.
Yeah, true that. So.
Yeah. And people are looking at those things kind of, you know, little, like, I don't know, call them chillers or not, but yeah, you always have the balance. Like if you're doing it, you have a brine or a glycol or something, you know, a heat transfer loop. You got to look at, you naturally lose some efficiency in each one of those heat transfer steps. So again, it's a balancing act. I think that was probably my conclusion for all the talking I did around the refrigerant fluids. You really got to balance a lot of different things. So yeah, those type of designs, you know, if you have to add a pump, that's going to add cost and maybe lose some efficiency. How does that balance out against going to a different fluid, maybe a more hazardous one that you want to keep more contained or remote? I think all that, I think it's still fertile ground for research. I don't know if there's any final definitive solution there. People are looking at it, and they should.
For the audience, you spoke a little bit about R32 and the discharge temperatures on the compressor. From an HVAC tech standpoint, or from an equipment manufacturer, not manufacturer standpoint, but is there a benefit there for higher discharge temperature?
I think if you can take advantage of it, probably, you know, in the heat reclaim side of things, it may be an advantage to have that higher discharge temperature. But you know, if you're not reclaiming it, then I would say it's a negative on your hardware and your system. But yeah, turning those disadvantages into advantages, I think, is what we need to do as an industry and continue to innovate and take advantage of those things.
Well, we certainly appreciate you being here today with us. This has been an informative, fear-removing, just an opportunity for me to educate myself on what's happening with this refrigerant change. And Dr. Allgood, I can't thank you enough for being here today.
You're very welcome. My pleasure. You know, Opteon.com, there's a lot of information on the transition, the regulations, the new products, training, etc. So glad to talk with you guys, and anything we can do to help, please reach out.
Super. So again, for the crowd, that was Opteon.com. Can you spell it for me?
Opteon, Opteon.
Awesome.
Yeah, definitely been very helpful, very enlightening for me. So thank you for your time. Thank you for your willingness to participate and to educate guys like us so that we can hopefully help educate some more people out there in the field as well.
All in this together. So.
Yeah, we are.
We're all in this together. So
all right, from the LG Procast team, thanks.
Have a great day. See you guys.
Thanks again. Bye-bye.